Okay, so we have talked about one type of word problem, the simple compounding interest problem. That's when we use this formula, where R is the growth rate or the decay rate, T is the amount of time that's passed, A0 is the initial amount. Now we're going to talk about a new type of word problem, and I'm going to talk about this one, and then we're going to talk about two others later today. This one is a half-life problem. So in a half-life problem, you're going to use a formula that looks like this, which I'll get back to, explaining what exactly all those letters mean. But first, let's just think about what a half-life actually is. So if a radioactive isotope has a half-life of 2 days, it means you decrease by 1/2 by a factor of 1/2 every 2 days. So let's make that clear with a table of values. So at time equals 0, in this case, we have 20 kilograms. 2 days later, you're going to have half of 20. So you're going to have 10. 2 days later from that, you're going to have half of 10. So you're going to have 5. 2 days later from that, you're going to have half of 5. So you're going to have 2.25. So this is an exponential function. It's an exponential decaying function. After 8 days, you're going to have 1.25. Again, just keep dividing by 2 each time. But what about if we wanted to know after T days or after 1,000 days? You're not just going to want to keep filling in this table of values forever. So that's when our half-life formula comes into being. So we are trying to figure out how much you're going to have at time T. Our initial amount is 20, so that's the same between these two formulas. This A0 is still going to be 20. And now you're going to put a 1/2 in your parentheses because it's halving every 2 days. So 1/2 goes in your parentheses. T is the same thing as our exponent up here. Basically how much time has passed. And then K is the length of your half-life. So in this case, the length of your half-life is 2 days. So you're going to put a 2 there. So this formula can also be useful if you're thinking about, like, if instead you had a radioactive isotope that doubled every 2 days, you would still use this formula. Or if it tripled, you're still going to use this formula. This basically is going to be, B is going to be 1/2 if it halves every X days. B would be 2 if it doubles every X days. It would be 3 if it triples every X days. A0 is still your initial amount. T is the time that passes. So how many days have passed? And then K is length of your half-life, or length of your doubling time. So I'm doing example number 4 is one that still uses this formula, but is a tripling time instead of a half-life. So the number of people with a highly contagious virus doubles, I guess this is a doubling time, doubles every 3 days. If one person has the virus on January 1st, write an equation for the number of people who've had the virus as a function of the number of days since January 1st. So we have AT. Our initial, well, let's just write out our formula first. Our initial amount of people who have the virus is only 1, so we put a 1 there. This is doubling. It's not halving anymore, it's doubling, so we put a 2 there. T is part of our function, how much time has passed. And then K, this happens every 3 days, so you're going to put a 3 there. Okay, so you can work with other people, but I want you to work through question number 1 on the homework and question number 5 on the homework. Talk to each other if you need to, or you can work alone. And then once you're done with that, come back and watch the second video, which will introduce 2 more formulas.